upon r square dou r plus 1 upon r square sin theta dou theta operating on sin theta dou theta plus 1 upon r square sin square theta operating on dou square phi. So these are some identities that we know. Similarly, del cross del or curl of the delta operator is equal to 0 because it is from A cross A is equal to 0. Based on that, del cross del is equal to 0. Then and now look at this coordinate system, Cartesian coordinate system and spherical coordinate system. Both you can see here. Here we have the x-axis along the horizontal axis, z-axis is along the vertical axis, and the y-axis is perpendicular to the xg axis and which is inward to the plane that you are seeing, this white plane or the paper that you see. Inward to the paper is the y-axis. Now in the Cartesian coordinate system or in any coordinate in this space, if I take a point, any arbitrary point, and then that point will have coordinates x, y, z. In the Cartesian coordinate system, its coordinate will be x, y, z. Now let us draw a perpendicular from that coordinate point onto the xy plane, and if it meets the xy plane at some point and the meeting point is connected to the origin, and this the line that is connecting the meeting point and the perpendicular the meeting point of the perpendicular and the origin. So the angle between this line and x-axis is called the angle phi. Similarly, the angle from z-axis, z is called the zenith direction. From the zenith direction, the angle towards the vector r, position vector r of the point, that angle is called theta. At this point, if I take a infinitesimal volume, then on the volume, if I draw a line which is along the theta direction, that line will be r d theta. If I draw a line which is along the phi direction, that will be r sin theta d phi. The line along the r direction will be dr, because all these d terms come because of infinitesimal size of the box. Now on the line that is dropped from the point to the xy plane, on that the line will make when we join that line to the origin and we have phi, so then because r is there, r is the position vector and theta is the angle of r with z, then the component or the projection of r onto the xy plane is the line joining the origin to the point where the perpendicular meets the xy plane. So that is equal to r sin theta. That is the projection of r onto the xy plane when r makes angle theta with the z plane. So that is r sin theta. Then r cos theta will be from the origin. If I draw a line, if I draw a projection of this projection onto the x-axis, that will be r cos phi or r cos phi sin theta. Okay, so from this, using this, we can write del dot as the operator. Del dot will be equivalent to 1 upon r square dou r operating on r square plus 1 upon r sin theta dou theta operating on sin theta plus 1 upon r sin theta dou phi. So these are the operators. Then del cross A will be in spherical coordinate system. It is a determinant of 3 cross 3 elements. The first row of the determinant is r cap upon r square sin theta. Second is theta cap upon r sin theta. Third element is phi cap upon r. In the second row, first element is dou r, second element is dou theta, third element is dou phi. In the third row or the last row, the first element is ar, second element is r a theta, and third element is r sin theta a phi. So these are some vector identities that we are going to use later today, and brief about the coordinate system, spherical coordinate system, and the Cartesian coordinate system. Now let us come to a typical radiation problem. Why we are considering a typical radiation problem? Reason is we are considering antennas, and antennas are typical radiators of electromagnetic waves. Therefore, we will consider a typical radiation problem. In a typical radiation problem, we impress a current distribution. So there will be impressed current distribution. If you impress a current distribution which is not a direct current or which is not DC, it is not a direct current, it is AC or alternating current. So if we have impressed alternating current distribution, in that current distribution, alternating current, once you have alternating current, that is resultant of accelerating charge. Charge is oscillating in the AC, therefore it is the resultant of an accelerating charge. Accelerating charge creates fields. So if we have an impressed current distribution, that will create field. These fields will have a certain field distribution. They will be distributed in the free space or in the space surrounding the current distribution. That field distribution can be described by Maxwell's-Kerr equations, or the Maxwell's-Kerr equation describe the field distribution due to impressed current. Which are the Maxwell-Kerr equation? These are curl H is equal to J plus dou TD and curl E is equal to minus dou TB. So curl H is equal to J. J is the current density or current distribution plus time derivative, partial time derivative of D. Similarly, curl E is minus partial time derivative of B. Now, if you look at these two are differential equations. These are first order differential equation because it is del cross, so these are first order. Similarly, partial derivative is also first order. So both these equations are first order differential equation. These are linear equation. There is no square term or cube term, higher order term. Therefore, these are all linear equations. Typical characteristics of this equation is each equation contains both fields. The first equation contains H and D. H is equal to B upon mu 0 or B is equal to mu 0 H. D is equal to epsilon 0 E. So the first equation contains E and H. Similarly, in the second equation, you have E and B. B is equal to mu 0 H. Therefore, the second equation also contains E and H. So both equations, they contain E and H. Since both equations contain E and H, these two equations are coupled to each other. They are not same equation. Two different equations containing two different quantities. Therefore, both the equations are coupled. So they are coupled to each other. If they are coupled to each other, then these are differential equations, and we are going to solve this differential equation. Then we need to solve them simultaneously. So we require a simultaneous solution of these two equations to find out the field distribution or distribution of E and H in space. If we want to find out the distribution of E and H, then we have to solve these two equations simultaneously. Simultaneous solution of two coupled differential equation is a difficult process, and mathematically or analytically solving this is very difficult. It is a difficult process. Now, on this difficult process, the solution, because it is a difficult process, we require some alternative approach to solve this. Instead of solving this coupled equation directly, we need to find out some alternative approach for solving these equations. So the alternative approach should be, we have to choose judicially the vector identities. First, we have to choose vector identities judicially so that we can convert these chordal equations to uncoupled wave equations. So that is the necessity of solving these equations. So the coupled equations will be uncoupled in terms of as wave equations by judicially or appropriately choosing vector identities. So let us look at how to choose these vector identities. This we have already discussed, but let me once more go into this. Let us start with electromagnetic potential. From that we will get electromagnetic potential. Some of the useful vector identities is, if I have three vectors A, B, C, then A dot B cross C is equal to A cross B dot C. So dot product and cross product, if they appear in one equation, they are interchangeable. Similarly, using this, let us take A is equal to delta, B is equal to delta, then del dot del cross A. So A is equal to delta, B is equal to delta, C is equal to little a, italic little a, then del dot del cross A, little italic a is equal to, by change, now change the dot and cross product, that will give del cross del dot A, that will be equal to 0 because del cross del will be 0. A cross A, that identity use A cross A is equal to 0. So del cross del is equal to 0, it will be equal to 0. Then on K cross L, this is another identity. Suppose K is a vector, L is a vector, K cross L is equal to M. If we get K cross L is equal to M, for K let us use delta, for L let us use little a, and for M let us use A. Then del cross A is equal to U. So let us write that way. Then what we will do is take a dot product on both the sides. Then del dot U will be equal to del dot del cross A. Now del dot del cross A, we have already seen del dot del cross A is equal to 0. So del dot U is equal to 0. So that implies that if we have del dot U is equal to 0, U, the vector U, is represented as cross product of or del cross A. So delta or curl of another vector. So vector U is to be curl of another vector. If U is curl of another vector, then del dot U is equal to 0. Or if del dot U is equal to 0, then U is curl of another vector. Similarly, let us see another identity. A cross AG. G is a scalar, A is a vector. A cross AG, that is equal to A cross A into G. A cross A is equal to 0, so that will be equal to 0. Now for del A, let us put del. So del cross del G is grad G. So curl of grad G is equal to 0. This is a vector identity that we already know. Now let us go and apply this. If we are going to apply this, we know from Maxwell's equation, divergence of B is equal to 0. Use it from the second equation, del dot U is equal to 0. Del dot U is equal to 0 implies U can be represented as curl of some other vector. Del dot B is equal to 0 now implies that B can be represented as curl of some other vector. Now we know B is equal to mu H. So we can write B is equal to mu H, and we can represent B as curl of another vector A. So B is equal to curl of capital A. Then from the curl of E is equal to minus dou TB. This we know, this is Maxwell's curl equation, second curl equation. So now write curl of E remains as it is equal to, for B we can put del cross A, and dou T is operating on only on T, del is operating only on A space. Therefore, they are interchangeable. Interchange dou T and del. So this becomes minus del cross dou T operating on A. Okay. Now take everything to the left side. So right side becomes 0, left side becomes curly plus curl of dou T operating on A is equal to 0. From that we take curl of E plus dou T A is equal to 0. Look at the last sign, last identity on the left hand side. Curl of grad G is equal to 0. Here we are seeing curl of E plus dou TA is equal to 0, which means E plus dou TA can be represented as grad of something, grad of a scalar. And so E plus dou TA is equal to minus grad phi. Why we are taking minus sign? That will be a clear letter. We also have already seen that why it is minus sign. So that will be clear letter. So we have got two things now. B is equal to curl A, or B is equal to mu H, which is equal to curl of A, and E plus dou T operating on A is equal to minus grad phi. So two important relations we have got. So this is one important relation, mu H or B is equal to curl A. Other important relation is E plus dou TA is equal to minus grad phi. Now this says that the divergence of H is 0, because divergence of B is equal to 0, so divergence of H is equal to 0. If divergence of H is equal to 0, which means H has no divergence, and that means H has only circulation. Why it will be only circulation? When divergence, nothing is going out of the H field, so H is to be conserved. When it will be conserved? If it is confined within a region, or it is rotating within a region. If it is moving, it is rotating within the region. Therefore, H has only circulation. Okay. So it is called a solenoidal field. Such field for which divergence is 0 is called a solenoidal field. It possesses only circulation, so H has only circulation. It can be represented by the curl of some other vector function. Here it is, the other vector function is A. A is called the magnetic vector potential, because it is related to the magnetic quantity B or H. So A is called magnetic vector potential. Usually we drop the word magnetic, we call A is the vector potential. The divergence needs to be specified for a complete definition of A. What does this mean? We now know that curl of A is equal to B, or curl of A is equal to mu H. But we do not know what is divergence of A. To specify A completely, we should know what is the nature of divergence of A also. So any vector can be represented if, or any vector is complete if we know what is its curl, what is its divergence. Its curl is known, its divergence is not known. We will see why that is required. So A is not unique unless we define the divergence. It is not unique. So del dot A is unspecified. That makes A ununique. A is not unique. We have to specify divergence of A. That we will see later how to specify it. And now E plus dou T A is equal to minus grad phi. If we take curl of both the sides, that is equal to 0. That we already have seen. If curl is equal to 0, then it is a conservative field because it is rotating. And so curl is equal to 0. It starts at a point, then it comes back to that point. And so the curl is equal to 0 gives you a conservative field. Dimensionality of both the sides, E plus dou TA, that is on the left hand side, and minus grad phi on the right hand side, their dimensionality has to be same. And on the left hand side we have E. Therefore, dimensionality of both sides imply that it is an electric field. This behaves as a static electric field. Minus grad phi is equal to 0 gives you a static electric field. Phi is called the electric scalar potential. Electric usually we drop, we do not use it, or phi we call as a scalar potential. Again here phi is not unique, it is a scalar which is not unique. We will take a break here. When we come back, we will start with Gauss transformation.